Last lecture on conjugate direction methods, our primary concern was how to find the conjugate directions, because we had already seen that if I know about the conjugate directions, solving a convex optimization problem, a quadratic convex problem with positive definite Hessian is a matter of n steps, but the question clearly lies at how do I find such a conjugate direction, and this method which we had written down in the last lecture, it was largely this was a method due to hastiness and Stiefel-Hastiness was responsible for a brilliant school on optimization and control at an optimal control calculus of variations at Chicago, and here we call this particular approach is called the conjugate gradient method. This is called the conjugate gradient method because my starting conjugate direction is minus g0. So, you see what we generate here, at least in the convex case, that convex quadratic case, that if I slightly tamper the idea of steepest descent method, then I can get an algorithm which is much faster than the steepest descent method, at least in the convex quadratic case. So, here because we our initial direction, initial conjugate direction is found by taking the negative of the gradient at the starting point x naught. G0, of course, in this case you might be wondering, G0 is actually nothing but g of x naught. Now, what Hastiness and Stiefel shows that if you can construct a new vector which is the gradient at f x k plus 1, which you can also write is as like that. So, once you know dk, you know x k, and you find the alpha k which is of this form, and then you get the x k plus 1. Now, your dk plus 1 to go from x k plus 1 to x k plus 2 is found from dk in this sort of manner. Now, the remaining question, the major part of the proof lies in the fact that this d0 d1 dot 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 dn, this series dn minus 1, this series of vectors are actually conjugate direction. That is, if we start to prove this thing, a proof methodology would first show, we have to show, essentially that is what we need to show, that d0, d1, d2 so on up to dn minus 1 forms a set of conjugate directions. And once I know that these are conjugate directions, then it is the same as what we had discussed before. And how do I prove that, and what I need to prove? So, what I want to prove is that I have to prove that di h dj, obviously conjugate directions with respect to h, because the original problem has the Hessian matrix as h, and of course, you have to consider this as positive definite, which I have already written. Sorry. So, H is my Hessian matrix, if you want to trace that at every point x. So, you should prove di h dj or dk h di is equal to 0 when k is not equal to I, but another way of showing is that this is equal to 0 for all I. So, you fix the k and you change the i's. For all I which is strictly less than k, this is equal to 0, and this is true for. So, if you can show this, then you basically show that d I in a product H d j is equal to 0 whenever I is not equal to j. So, if k is 1, then you put d 1 H d 0, if k is 2, then you have 0 and 1. K is 2, then I is 0 and so possible values of i's are 0 and 1. So, it will be d 2 H d 0 is 0, d 2 H d 1 is 0. So, in this way you basically show that d I H d j is equal to 0 when I is not equal to j. So, what would be our proof approach? In this part, when you have these sort of things, when you have to prove something about a large number of elements, you use the method of induction. You prove for the two of them, and you prove for 3, and then you prove for k, then you prove for k plus 1, and that is what we are going to use here, the method of induction. So, by the method of induction, what are we going to show? We are going to show the following. We are going to say that okay, I will assume that this is equal to 0. So, we assume for every I which is bigger than or equal to 0 and strictly less than k. So, once I know this, what I have to show that so this is what I have to show. And that is exactly your induction step. So, this is your induction step. So, once this is known, let me try to use it now. Now, let S V 0, V 1, V k denote the linear span or the subspace, whatever linear span is a subspace or the subspace spanned by the vectors V 0, V 1, V k. So, what do I mean by this term spanned by the vectors V 0, V 1, V k? So, you say that any vector say V is element of the span, or you sometimes they write LS linear span or just L span of this So, V is this if and only if this is a symbol of if and only both ways. V can be written as summation alpha I V I is equal to 0 to k, where alpha I is in R. That is, any element in this space can be written as a linear combination of the elements V 0, V 1, V k. So, that is the meaning of linear space. Now, G k is grad of f x k, which is h x k plus b. So, g k plus 1, which is grad of f x k plus 1 is h of x k plus 1 plus b. Naturally, g k plus 1 minus g k is h of x k plus 1 minus x k. Now, you know that if I go back to this setup, x k plus 1 is written like this. So, x k plus 1 minus x k is alpha k d k. So, it is also g k plus 1 minus g k is alpha times h of d k, because x k, since x k plus 1 is x k plus alpha k d k. Sorry, here I should put alpha k. So, this is what you have actually. So, this is the basic stuff we have. Now, let us see what does this show. So, if I put k equal to 0, then I will have g 1 for k equal to 0. It implies that g 1 is g 0 plus alpha 0 h d 0. G 1 is a linear combination of g 0 and h. Now, since d 0 is minus g 0, I can write g 1 as g 0 plus alpha naught h. Now, you have to put minus here, because d 0 is minus g 0, that is the basic assumption, that is how you take the starting one. This is exactly this assumption, and which we will now try to write down here. That is what you have at this point. Once you have this, I can keep on doing the stuff. Now, if I look at d 1, the direction 1, it is minus g 1 plus beta naught d naught, where d naught is again minus g 0. So, now g 1 can be written as g 0 and d 0 can be written as minus g 0. So, b 0 g 0. So, g 1 is g 0 minus alpha naught h g 0. So, it is 1. So, I have minus g 1. So, minus g 0 plus. So, I will have plus and minus g 1 is minus g 0 plus minus g 0. So, that is what we will have. So, now I can write minus 1 plus beta naught. Okay, beta naught is the beta naught here. Beta naught is a beta naught that you already know here. This is a beta naught. This is actually scaling up and generating the descent directions, the conjugate directions. I can write this as this into g naught plus alpha naught h g naught. So, d 1 is the linear combination of g naught and h g naught. So, let us for k equal to 2. So, what I have, what I have concluded here. So, g 1 and d 1 are the linear combinations of this. D 1 and g 1 are linear combination of g 0 and h g 0. Now, I leave it to as a homework to prove. Now, what we will have here is S now, this I of course, what we are trying to show that the linear span or the subspace generated by these two are same as this two and same as this two. So, this is a simple exercise in linear algebra which I pose as homework for your course. So, you have to show this as a homework. Now, let us look at k is equal to 2. Cut for a minute. So, for k equal to 2, we can again write G2 as G0 minus alpha naught plus alpha 1 into 1 plus beta naught into H G0 plus alpha naught alpha 1 H square G0. How to compute this G2 is again by putting k equal to 2 in the expression of gk plus 1 is equal to gk plus alpha k h dk, and then successively suppose G2 is G1 plus alpha k h dk h d1. So, you put what is d1 and g1 in their place, you will get this expression. So, I will ask you to check it out as homework. Check it out. So, it is your duty to check it out whether what we have written on the board is actually on the screen is actually correct. And now D2, so here G2 is a linear combination of G0, H0 and H squared G0, and so D2 is written as so the coefficients are getting slightly complicated once we introduce the other variables. So, if I know the gradient vector at this and this gradient vector at G0, that is x naught, then I can have a lot of information about the problem. So, here beta 1 beta naught are calculated accordingly to that beta k formula given in the beginning. Now, what I want to say is that you observe again that G2 is a linear combination of G0, H0 and H square G0, while D2 is also a linear combination of G0, H0 and H square G0, which shows that then from there you can have this conclusion that the span generated by G0, G1, G2 is same as the span generated by these vectors. So, again the span generated by, see our whole goal now is we are trying to prove that these are conjugate directions. You see how much work is involved. It is very easy to state the theorem, anybody can understand possibly who has done a bit of optimization, but the problem lies that once you start proving that there are conjugacy of the directions, then the difficulty starts. Now, this is also equal to the span of so that is what happens. So, Now, if you continue in this way for say k steps, k minus 1 steps essentially, k steps essentially, then you will have the following by continuing. So, we know the result up to k. So, let us go up to k by continuing in this manner. That is, you see what we did was d1 was a linear span of 0 g0 and hj0. Then we expressed d2 in terms of d1 and pressed back the value of d1 to get g2 and d2, and now in the there are 3 terms now g0, h0 and h squared g0 expressing g2 and so is d2. So, what we found is these two. So, these two you have to again find as homework, it is not very difficult, it is plain simple manipulations. And by continuing in this manner, so I am continuing in a manner same as what we have just done here, and if we do so, then I can extend these things. So, our stuff is up to k, we do not know what is there in k plus 1, that is exactly what we have set out to prove. This is true, and of course, once you know this, you can of course extrapolate and say that this is true, then sorry not G, I made a mistake, the directions. Is same as this. So, the thing in the top part of the board and the bottom part of the board looks similar, but it is enough that if you prove the top part, once you prove the top part, you can understand the bottom part, it is just an extension of that. So, once I know that, I now start doing the stuff. Now, what I can now look at this expression, what I have to compute is for I, for any I which is strictly less than k plus 1, what I have to compute is let us see how to compute this expression. Now, dk plus 1 is of course minus gk plus 1 plus beta k dk. So, what I get here is minus gk plus 1 h d I plus beta k d k h d I. So, now what I do is to restart this thing and look at, okay, I am looking for I strictly less than k plus 1. So, I can choose I equal to k. So, put I equal to k to get now what happens to this, that is a very important thing to know. Now, if I put I expect this should be 0, but let us see what happens. If I put bk's expression, this one, so now bk would become so what happens is that you see this gets cancelled with this and this. So, this remains and which is nothing but the negative of this. So, ultimately this becomes 0. So, that that is what that is why the choice of beta k is particularly important, and that comes out in a very natural way. So, now which I leave for you to think about how did people conjure up this expression for bk. It has got linked with what we had discussed in the previous section. Okay. Now, here we have this part. So, this part is 0. So, now we have to look at scenarios where k is strictly less than 1, I is strictly less than k. Now, consider now if I do that, if I take now consider I is strictly less than k. Now, using these facts which are already written down on the board, using these two facts, I expect you to show that this is a simple exercise in linear algebra, and so I think this practice is important when you learn on constant minimum optimization. So, prove this, show this as homework. Now, once this is true, actually HDI can be shown as a combination of G0, G1, G2, GK and all those things. So, then you can basically show that because this is equal to this. So, you through this, so which means this is equal to this and this is equal to this. So, this is equal to this. So, HDI becomes an element of that, and so hence we can show that HDI can be written as HDI yields, you have some scalars AI. So, I is equal to 1 to k. This is how it happens, linear combination of this. where ai with I from these are constants. And now once I know this, then I can go back to this part, because now I have to look into the case I strictly less than k, because for I equal to k I know that dk plus 1 h dk is 0. So, this can be again written as, because of h di is minus a I di. Okay. Now, what I want to, how do I prove that? I need to prove that this is 0. So, how do I do this? So, I will write down h di is so this goes the calculation. Now, what is dk plus 1? Dk plus 1 is nothing but minus gk plus 1 plus beta k dk. And this into ai di. This will give me I is equal to 0 to k. If I break it up inside, this is minus gk plus 1. ai of course is a scalar which I can write in the front. If so, I can take this scalar out, and so I can have ai times minus gk plus 1 di plus bk times ai dk di. Now, for this, to prove this 0, we need to go back to the homework that we gave in the last lecture. So, consider that. So, how to prove this 0? See, now you observe that. So, in the same problem I have asked you to show that gk di, where di are conjugate directions, is equal to 0 for. So, up to k I have conjugate directions. So, gk plus 1 di I is strictly less than k. So, is strictly less than k plus 1. So, this is 0, right. So, this becomes equal to 0 because of this assignment. Just go back and try to see. So, if each di is a, so if I have kept here gk plus 1, then I have di, where di's are behaving as a conjugate direction till k, then this holds true. Okay, so I go back. So, using that particular thing, this becomes 0, while I think there is a small little bit of change I will do in the calculation. Let me rub off this to make it much more effective. Let me not put AIDI here, just I am going to change the calculation. So, let me do something here. So, what I do is I first take the dk plus 1 and write it as minus gk plus 1 plus beta k into dk, and that I put with HDI, because then I can have minus gk plus 1 h di plus beta k dk h di. Now, this is 0 is already known, that is the assumption we have made, and here I will have, by putting h di is this, I can write this part only as I equal to 0 to k ai into gk plus 1 di. So, we know that from, again I go back to this homework, where is that? So, whenever k is bigger than this I, so k plus 1 is bigger than I because I is strictly less than k, then this is always 0. So then using that fact, we can now conclude that this is 0 and this is anyway 0 because that is the assumption. So, what I have is that this is 0 and what I have is that this is 0. This is 0 from the homework and this is 0 from assumption. So, ultimately you have dk plus 1 h di is equal to 0 for I strictly less than k, bigger than or equal to 0 of course, but and with k I have already proved. So, what we finally proved is that dk plus 1 h di is, so this would imply finally that dk plus 1 h di is equal to 0 for I strictly less than k plus 1 and hence we have proved this thing. Okay. So, added with this result, this result has two parts, is this result. In our next lecture we are going to prove this part and we are also going to complete the homework that I had given. We are also going to complete this homework, where is it? This homework, as well as we are going to complete the proof of this part. Once we do that, we will write down the conjugate gradient algorithm, and once we do that, we will stop our discussions of conjugate gradient algorithm for the moment and then go on to study what is called quasi Newton method. You see, the proof here rests largely on the fact of the clever use of identifying two types of subspaces generated by very different sort of bases. So, basically you are finding a subspace, the same subspace, but with different bases. So, these writings here, you have the same subspace, but here this is the basis and here this is the basis. So, this is generating this and this is generating this. Okay. So, we end our talk today, and first in the next lecture we are going to first concentrate on proving the B part of what is left, and then, which is also very important to know and it is not a very trivial proof, and once we do that, then we can write down the conjugate gradient algorithm, but before that we will also complete the solution of the homework that we had given. So, with that we finish our talk today. Thank you very much. Please go through these calculations very carefully, because conjugate gradient calculations, though they are simple, they are not so straightforward, because really you really have to do these linear algebraic manipulations to show that, and I expect that you really take some time to have a look at these things. Thank you.